Today we'll talk about nuclear fusion. Nuclear fusion is the name for the combination of small atomic nuclei to create a larger nucleus. Nuclear fusion is only possible when there is enough kinetic energy to overcome the electrostatic repulsive forces between two positive nuclei, and be forced close enough for the attractive nuclear force, the force between two or more nucleons, to be strong enough for nuclear fusion. Nuclear fusion is a wonderful alternative for fuel source as compared to nuclear fission. This is because nuclear fission creates a lot of waste product with a larger proportion of neutrons than ones in a stable nucleus of a similar atomic number. This causes the waste product to be unstable and thus radioactive, whereas nuclear fusion forms harmless waste products like helium from the fusion of hydrogen nuclei, or carbon and oxygen from the fusion of helium. Presently, we are unable to use nuclear fusion in power stations on Earth. This is because it requires temperatures and pressures too high to be safely contained by any physical material in the world. This is because it requires at least 1 mega electron volts of kinetic energy to acquire nuclear fusion. However, there are many experimental reactors in the world, like the Joint European Torus jet, that utilize strong magnetic fields, also known as magnetic confinement, to contain the fusion fuel in the form of plasma. Problems with these reactors is that they cannot generate electricity, as it takes more power to acquire the temperature than the reactor can produce. Scientists at the National Ignition Facility, NIF, have undertaken a different approach to achieve fusion. They utilize 192 laser beams from the world's most powerful laser to heat and compress a small pellet of hydrogen fuel to the point where hydrogen fusion can take place. Nuclear fusion is also known to take place in fusion bombs, like the hydrogen bomb, where the temperature and pressure required for fusion is acquired through fission reactions. Research on cold fusion, a way to perform nuclear fusion at room temperature, have been proposed in 1989 by Stanley Pons and Martin Fleischmann, reporting of apparatus that produced anomalous heat. However, many scientists have tried and failed to reproduce these results, and finally cold fusion was deemed unacceptable as a realistic method of energy production. Fusion in stars. Stars are born from a cloud of dust and gas that contract and clump together due to gravity over a long period of time. When a cloud clump gets dense enough, they fragment into different regions called protostars that separately contract and heat up. Eventually, the temperature at the core reaches around 1 mega electron volt, and nuclear fusion of hydrogen to form helium occurs. The energy released from hydrogen fusion in the core, also called core hydrogen burning, creates enough pressure to prevent further gravitational collapse. And at this stage, the protostar becomes a main sequence star and will remain in this stage for most of its lifetime, relatively unchanged as nuclear fusion continues to occur. When the core runs out of hydrogen, the core contracts due to gravitational collapse and heats up under the weight of the star. The heat of the core heats up hydrogen atoms surrounding the core and causes them to undergo hydrogen fusion. This is called shell hydrogen burning. At this stage, low-mass stars tend to use up their fuel and fade away after the shell hydrogen fuel runs out. For higher-mass stars, when hydrogen at the shell runs out, the core collapses further, and when the heat of the star exceeds 100 million kelvins, helium in the core can fuse to form carbon and oxygen. This is known as core helium burning. Core helium burning releases huge amounts of energy, and this energy pushes the outer layers of the star outwards. The outer layers cool, and the stars become a red giant. For high-mass stars, it becomes a red supergiant. When helium runs out, the core contracts again and heats a shell around it to temperatures high enough for helium to fuse. This process is called shell helium burning. When the carbon-oxygen core is not hot enough for any further fusion, the star continues to contract due to its own gravitational pull, until it is halted by the pressure arising from electron degeneracy power. As the core contracts, the helium shell becomes more and more unstable, and the star pulsates and ejects its outer layers as a planetary nebula. The hot and dense core that is left behind is called a white dwarf, and it will simply cool down and fade away. However, that is only applicable for stars that do not have a large mass. If the mass of the core of the star is more than 1.4 times of the Sun, electron degeneracy cannot stop the core from contracting. In this case, electrons get squashed into the atomic nuclei and combines with protons to form neutrons and neutrions. When this happens, the core collapses and forms a neutron star. Neutron stars are generally very small, around 20 km across, and can spin really fast as 600 turns per second. Some neutron stars emit 2 radio waves as they rotate, and when these radio waves sweep past Earth, it is observed as a radio pulse. These rotating neutron stars are called pulsars. The outer layer of a neutron star usually falls into it and rebound. The rebound causes huge shock waves, which effectively rip the star apart, causing a supernova, whose light can briefly outshine an entire galaxy. If the star's course is 3 times the mass of the Sun, even the neutrons cannot overcome the gravitational pull, and the star collapses into an infinitely dense point called a singularity. The singularity can pull in everything, even light, within a distance called the Schwarzschild radius, in which its boundary is called the event horizon. This phenomenon is what we call a black hole. All elements are formed from nuclear fusion. This process is called nucleosynthesis, which creates new atomic nuclei from pre-existing nucleons, primarily protons and neutrons. The first nuclei created was from the Big Bang nucleosynthesis, which formed hydrogen and helium. From these first 2 elements, all the other elements were created through the fusion within stars. However, under normal circumstances, only elements up to iron can be formed, since the fusion of iron is practically impossible. This is due to the term called iron peak, which tells us of the energy release ratio between nuclear fusion and nuclear fission. Elements before iron release energy from nuclear fusion. However, elements heavier than iron consume energy in nuclear fusion, which makes nuclear fission more favorable as it releases energy. Therefore, in normal fusion in stars, fusion is only possible up to the element iron. Heavier nuclei are created in supernovas when a neutron star is ripped apart by pulsation.